Hello everyone. This week we're going through a few algorithms related to string manipulation. And the first one is a topic that should be very familiar to you, the longest common subsequence. But before we start, let me summarize one more time what we've done so far and how you should see the second half of the semester. In the first half, you've done all the theoretical stuff. We look at brute force, we look at dynamic programming and greedy algorithm, but we did this in a more general point of view. Sure, you saw examples, but they reinforce the concept. And in fact, some examples are trivial, like we did linear search when we discussed divide and conquer, and we did linear search in a funny way anyway. So now we're going to the specific algorithms. That's what the second half is going to be like. And you will see that actually most of them fall into these three topics: brute force, dynamic programming, or greedy algorithm. And we're going to apply the concepts that we've learned. We're going to apply overlapping subproblems, optimal substructure. We're going to be seeing all that again. But the focus is now on the actual algorithms, not the theory behind them. This week we're going to look at three algorithms. Well, I guess just two, because this one you've seen before. We did this in week 4 when we discussed dynamic programming, because this is the main example of dynamic programming back in COM 225, COM 2010. So at this point, I really expect that you understand LCSS, and so we can talk more advanced stuff about it. But let's always start with the definition of what LCSS is. You have two sequences, x and y. I'm going to write like these: x, y, x2 dot dot xm, and then y1, y2 dot dot yn. And let's just use an example. Let x be kitten and let y be sitting. And the sequence ITTN is a solution. You can see that ITTN exists in both strings. And always, when you start doing something, yes, you know the good way of doing this. You know how to do this in dynamic programming, but always think about how to do it using brute force. See, I always use brute force as a starting point because I think it's good practice. The main idea is, if you do something by brute force, sure, it lets you think about how to make it run more efficiently. Like I said, brute force is normally the starting solution. But if you can see how you can go from brute force into an efficient solution for one problem, then maybe you have another problem with a similar brute force pattern, and that makes you realize, oh, I've done this kind of problem before. I didn't have to use brute force, I can apply this method. So maybe I can apply the same approach for this problem. You see what I mean? If you only look at the efficient way of doing something, then you miss that improvement from brute force to the good method. So how do we do this using brute force? Because sometimes it's not that easy to work out the brute force method. But this one should be pretty simple. You have two sequences, x and y, of length m and n, respectively. So you just generate all subsequences of x, and then you generate all subsequences of y. That's 2 to the m and 2 to the n combinations. So you have to compare every single subsequence of x with every single subsequence of y. And complexity is going to be 2 to the power of m plus n. Great. Exponential complexity, surely we can do better. Now, how do you go from brute force to dynamic programming? Well, you try to find the overlapping subproblems, sure. And like I said earlier, use brute force as a starting point. So what is it that you do in brute force? I'll be comparing all these subsequences. So let's say I take kit, K-I-T-T, and I'm going to try to compare it to y. I'll be compared to something like SITT, SITTI, SITTIN, and SITNG. So hopefully you can see here that there's a waste, right? Do you need to keep on comparing k? Can you drop it? Like, if I'm comparing KITT with SITT, and I know k is not going to help me, so can I just drop it? Meaning that I'll be comparing ITT with SITT instead. But same thing with S. Can I just drop S? If I compare ITT with SITT, and the S doesn't really do anything, so should I keep on comparing ITT with SITTI, and so on? And how about now if they're both the same, like you have IDT and IDT? Is there any point in me comparing IDT and IDTI? So that's the benefit of doing brute force for me. I like to look at some sample inputs, think about how I would solve it, and then see if I'm doing anything wasteful. And here I actually see some pattern that I can use to save some computations, right? I notice that if the first characters of both string matches, then I'm going to take them off. What do I mean by taking them off is I'm not going to compare them again. I'm just going to move on to the next character. If they don't match, then should I keep both? Well, if I keep both, we'll never progress. We'll never go to the second character. Should I take both off? Well, no, because if I take both off, then the second one, like the first character and the second one may match another character on the first one, or vice versa. Should I just take off one from one string or the other string? Yeah, because clearly the character that you have is not helping. That's what I mean there. Because the character at the start is they don't match, so why would you give them round? So you take it off. But see, here's the rub. This is still brute force. It's just that I'm being a bit smarter about it. Alright, if I know the first character doesn't match, then it's a waste keeping it around. But I'll still try both combinations. So here, kitten and sitting, I know K and S, they don't match. So I get rid of K in one by going to the left here, and I get rid of S by going to the right. So eventually, I'll still try every single combination. Of course, you have the second case here when they actually do match, and in that case, I'll just match them up. Here is the recursive relation written more formally. So as before, if the first characters do not match, then I'll get rid of them. Going to the left, I'll get rid of x1. Going to the right, I'll get rid of y1. And if they do match, I'll still get rid of both of them. And that's going down. Or here is the recursive relation written. Something that you've probably seen in week 4. I think I had that in week 4. So obviously we don't do anything if either string is empty. So the longer sequence is going to be 0. Or if they don't match, the first characters don't match, then it's not going to contribute anything. But if they do match, I'm doing 1 plus the subproblem. And there's a subproblem here of the string starting with the second characters. You see, this is still brute force. If you try to run this, if you try to run this code with a big enough string, it'll go on forever. Because it still is brute force. It will look like this when you break it down into problems and subproblems. Right, so every time I go to the left, I get rid of x1 or the first character in x. If I go to the right, I remove the first character in y. Well, I don't have any arrows going down, but still, you see how they overlap, these two. Right, so the dynamic programming comes from realizing that, hey, they overlap, so we don't have to do them both. And if you want to find out more about that, we talk about that in the week 4 lecture, so go check it out. Here's your example with kitten and sitting. Well, there's one arrow going down here when the eye matches, and I guess this will go down again. We'll talk more about the top down and the bottom up at the end of this lecture. But before we go there, let's discuss the optimal substructure. As in, does the longest common subsequence problem have an optimal substructure? Well, we saw that it does have overlapping subproblems. Now, does it also have optimal substructure? Let's prove it. And I took this proof from the textbook. Can't remember the page, but it's on chapter 15 about dynamic programming. So you can refer to it if you need more information. So as before, I'm gonna define x and y as the two strings, and then I'm also gonna define z to be the longest common subsequence of x and y. Remember, we're trying to show that LCSS has optimal substructure. And the way we do it is always the same. It's the cut and paste technique. The way it always works is that we assume we have the optimal solution. In this case, we have Z, right? And then we're going to prove by contradiction that the solution to the subproblem must also be optimal. So we have two different cases now. We have the case where x1 doesn't equal y1, so the first characters are different. So we're going to say that Z is either the longest common subsequence of the subproblem. This is the first subproblem. Like I'm going to the left. Oops. And sorry, or Z is the longest common subsequence of the second subproblem of we going to the right, so we get rid of y1. That's the first case. The second case is if xy matches y1, if x1 matches y1, then Z should contain x1, which is the same thing as y1. In other words, like Z1, the first character is that character, x1 and y1. And then Z2 is the longest common subsequence of x2 and y2, like the remaining subproblem. Okay, so these are the two cases we have to prove. All right, let's look at the first one. Okay, first one here, the first characters do not match. So either that Z is the longest common subsequence of the left subproblem here, or it is the longest common subsequence of the right subproblem. Now, one more time. Z is the optimal solution to the whole problem. Z is like the optimal solution of this kitten and sitting. All right. So how do we show that this has optimal substructure? Well, we claim that Z must also be the optimal solution to either this subproblem here or that subproblem there. It's got to be one of them. We pick one, which is the best. We find the maximum of these two. The argument is always the same. It's always by contradiction. So if somehow Z is not the longest common sequence of x2 and y, or of y and x2, like so, this is symmetrical, that means there is a longer common subsequence than Z. Right. So so Z is not the longest at this point here. Like you found you got to answer Z and you find a better answer. So obviously that better answer is also better up here. So that can't be right because we claim that Z is the optimal answer. So same cut and paste algorithm as before. All right. So if Z is the optimal and solution to the problem up here, then Z must also be the optimal solution to one of these subproblems. You have optimal substructure. The second case, what if the first characters match? Then we claim that Z1 must be equal to x1, or also equal to y1, I guess, and that Z2 is the longest sum subsequence of x2 and y2. Don't think I defined this earlier, but sorry, yeah. X2 and y2 is just the string x starting from the second character, and y2 obviously the string starting the second character. Right, so that's your subproblem here, just going down. Okay, again, we prove this by contradiction. This one is slightly different. We're trying to show two things here. We're arguing that this case also has optimal substructure, yes, but also that x1 must be in Z. And that's the first point here. If x1 is not in it, then remember, the subproblem is we get rid of both x1 and y1. We decided to do this earlier, right? So if you don't have x1 in the optimal solution, then I can just add it in, right? X1 matches y1, and boom, I have something longer. So your optimal solution cannot not contain x1, right? So Z must contain x1. For the optimal substructure, it's the same exact argument as before. So we have the subproblem where we got rid of x1 and y1, so the solution is Z2. If Z2 is not optimal, then there's a longer one, Z star or something. Then again, I just add x1 to it. And voila, I have something longer. I have a better solution than the optimal solution. So it does have optimal substructure. Right, remember, optimal substructure means the optimal solution contains the optimal solutions to the subproblems. I feel like these proofs are sometimes hard because it's very obvious. It's like you're trying to argue things which are obviously true. And we've done this so many times. Hopefully you're used to it by now. And in general, look, it's always the same cut and paste argument. You have minor changes here and there, but the idea is always the same. Right, let's talk about how to write the solution for LCSS. The solution is just going to be based on the recursive relation that we saw before, this one here. But remember, this is brute force. This is still brute force. If you try to run this, it'll take forever. Here's the code. As you can see, it matches. Here's the first case where both strings are empty. Or, sorry, if one of them is empty, so it just returns 0. And here's the case where they match. So when they match, you just do 1 plus recurse on the substring. If they don't match, you take the maximum of either take one character from the first string or take one character from the second string. That's it. Like the top-down version is very easy to write. The only difference between this code here and brute force is the addition of this if statement here, line 5 and line 6. As in, if you have computed before, don't recompute it, just return it. And also the fact that you store the answer somewhere before you return it. But if you know the recursive relation, you can write the code easily. That's just how DP works most of the time. Bottom up, it's going to be a bit more work. Remember, the idea of bottom up is that when you're doing top down, you're going to go all the way to the bottom anyway. And you're going to need every single node. So might as well compute them at the start. Right? And as before, you see that this shape, even though it's a tree, they have so many overlaps that they form nicely into a 2D array. And that is how we're going to make our bottom-up solution. We're just going to make a 2D array, but instead of computing from the top left, that's where the answer is going to be. We're going to start working from the bottoms, so from the right side and the bottom side. So that's your 2, 4 statements here. And I'll let you work out the code yourself. This is basically just the recursive relation that we had before. Alright, so we start with all zeros here. We fill them up. How do we fill them up? Well, if the first characters don't match, so this is G and K, if they don't match, then you just take the maximum of the two subproblems on the left and the right. So these are these two. If they do match, like this one here, you have N and N matching, you take 1 plus the solution to the subproblem if you go down. So remember, like going down is like going diagonal now, and going left means going down, going right now. You get the idea, hopefully. All right. So, yep. So it's actually very, very easy to do this. And back in COM25, COM2010, I see a lot of students who can do the longest common subsequence easily. I mean, here's a graph, go do it, done. They can fill it up, they know how to fill it up, but they don't really understand what's going on. So now, hopefully, you do. So that's pretty much it for longest common subsequence again. And hopefully you pick up a few things. We're talking about brute force again. We talk about optimal substructure. And I'm going to end this lecture here. So I'll see you in the next one when we're going to talk about another string algorithms.